All right. This problem is trying to figure out the heating of water barrels that basically absorb the heat of the sun, and they're at 10 degrees Celsius after absorbing all the heat, and then they cool off to 0 degrees Celsius and then freeze. And while it's doing that, it's giving all of the energy that goes in this process. So it's releasing this energy that was stored in the barrels to the greenhouse. So there's a greenhouse that's trying to stay warm, and it's cold out. But instead of using electrical energy, it's using heat energy. Now, the important piece here is that the water, when it's cooling off, is going to utilize this equation that we use for heat, Q equals mc delta T. And this is a chem equation. So this is a review from chemistry. If it says you have 660 kilograms, that's your mass. Now this C is the specific heat of water. And if you don't remember that, it happens to be 4186 joules per kilogram. And that's going to cancel out the kilograms there, times degrees Celsius. Joules per kilogram degrees Celsius. And then the temperature is going to go from 10 to 0. So the final temperature is going to be 0. And all this Q is going to end up being negative, but I'm just going to make it a positive because the change in temperature is going to be 10 degrees Celsius. Because what we're ultimately trying to figure out is the total energy transferred. It will be negative from the water barrels, but then it's a positive change in energy to the plants, to the greenhouse itself. So if we multiply these three, we'll find the heat energy that's released during that process, which is the cooling off process. So 660 times 4186 times 10, and you get a number that is quite large, 27600. So 276,276,000, which is, let me look here, 27,627,600 joules. But that is not the only energy that is released, because not only does the water do this process by transferring energy from 10 to 0, but it also freezes. So we have to remember another equation from chem, which is Q equals mHF. Now I do HF for heat of fusion. There's different ways to denote heat of fusion, but it's basically the mass of the water times the energy required to freeze the water. That's called the heat of fusion. So 660 is the mass, and in chemistry it was probably either calories or maybe grams was the unit of the mass. But in physics we stick to kilograms and joules, and the value is quite large. It is 3.33 times 10 to the 5 joules per kilogram. That will also cancel out the kilograms, and you'll be left with a number in joules. 660 times 3.33 E5, and you get another large number, 219780000 joules. So if I look at this one, that ends up being 219,780,000 joules. So the total energy right here is, I'm just going to add the two numbers together, and you get, and I guess I'll put it over here because we got room, 247,407,600 joules. That's the total energy. Now, why does that matter? Well, that matters because that energy is going to be replaced with an electrical heating system. So this is how much energy would it cost to, or use to do the same thing electrically instead of using the power of the sun. So what we need to do is try to figure out the electrical equivalent of this. So what we need is we need to take that total energy and relate it to electricity. So here's the relationship to what we're doing now. The chemistry part obviously was review from chem. I put this problem on here so that you could see the relationship between things you already know and the stuff we're learning now. But if you think about it, energy is power times time. So this number here, 247,407,600 joules equals P times T. So we could find the electrical power, and then given the information we have, we can probably find the current that we ultimately want to find. Now this occurred in the problem that said it occurred in 9 hours. So if we take 9 times 3600, we have the total number of seconds, which is 32400 seconds. Dividing that into this, so taking that number, dividing it by 32,400, we get the total power of this system, which is 7636.04 watts. Now, there are a couple of equations for power electrically. Powers work over time, but when we're dealing with electricity, we have to figure out what we know. And we know the voltage is 240. So this is the same kind of voltage that a dryer or a stove would use. And we want to find the current. Now the equation for power when it deals with voltage and current is P equals VI. So 7636.04 watts equals 240 volts times I. So if I divide that number by 240, we get the current has to be 31.82, if we round, amps. Which I would just round to 31.8, but it was 0.816, so I'll round up to 2. So the current is quite high. So using the power of the sun, we get all this energy, and then if we want to convert it to an electrical system, we need to have a 240 volt power supply and a 31.82 amp current flowing through it. We could even figure out the resistance of the circuit that would be required for the heater, but it was asked in this case to find the minimum ampere rating of the electrical heating system. So there's our answer, 31.8 amps. And that's it.